You tell me when it's, oh yeah, there we go. It seems to be recorded right now.
Perfect.
Erik, thank you very much for introducing me and also for, together with Leo, inviting me to this fantastic series of lectures. I'm really happy to present my work here to quite a big audience. So good afternoon or good morning whenever you hear it, or good evening. And you just triggered me with saying he is, as far as you know, from the Max Planck Institute for Sustainable Materials. And indeed, this is of course correct. Wait, I need to say here one, okay, right. Probably many of you know that we were, and I was, for a long time at the Max Planck Institute für Eisenforschung, for iron research. And about 1 year ago, we changed our name to the Max Planck Institute for Sustainable Materials, or in German für nachhaltige Materialien. And unfortunately, I haven't put a slide in on the topics which we are going to look on, like how to reduce the environmental impact when creating materials, how to create materials which are good for electrification of the society. That means magnetic materials, for example, soft and hard magnets. There is a large number of research projects where we are interested in reducing the impact of materials on our planet, and that means making materials sustainable. And that is the larger topic of this. And of course, steel is one of them. Steel is one of the important impact materials for our environment, and reducing the impact of steel by maybe making leaner alloys, by creating it in a cleaner way without carbon dioxide production or whatever, is one of the severe topics. And it's a topic which is also continued from our former Institute for Iron Research. Now, what I'm going to talk today about is a technique which we are using to study all these materials, and that is actually electron channeling contrast imaging. And I called my lecture bringing the TEM to the SEM. And you will see we are actually seeing very similar pictures or images as we are used to from classical diffraction-based TEM, but in an SEM using this technique. The co-workers who have contributed to this work will be introduced in the course of the presentation. So let me very quickly go through the outline. I will first motivate, in an introduction, I will motivate why are we interested in this technique, ECCI, electron channeling contrast imaging, and very quickly show which kind of diffraction techniques are available in the scanning electron microscope and how they work together to bring this ECCI to work. Then I will go a little bit through the theory and show a couple of equations, not going into details, however. And after that, we will apply the theory to see actually what we are interested in, namely defects in materials, stacking faults, dislocations, nanotwins, whatever is available in extended defects. And very, very shortly, I address also the modeling of these defect images. And then I will illustrate all that with examples. And here is just 2 examples, but I have a number more, and it depends on how quick I am, whether I can show them all to you or whether I stick with these 2 major examples here. And finally, conclude that. So let me start with this first a statement. What is ECCI? So I mentioned already, controlled electron channeling contrast imaging is the abbreviation of ECCI with a little c in front of it. I could say ECCI is an old technique in scanning electron microscopy. It's actually one of the earliest contrast mechanisms which have been used in scanning electron microscopy. And my contribution is particularly this little c here. That means, how do we control the contrast, as we know it from TEM, to actually optimize the crystallographic imaging of defects? So it is clear this is an SEM-based electron diffraction technique. And as we are talking about electron diffraction, we are, of course, using backscattered electrons. That means electrons which have lost almost no energy when they are traveling through the material. And we use these backscattered electrons with ECCI to see lattice defects as we do it in TEM. And now the next step is, if we control the illumination, that means we control the tilt of our sample with respect to the electron beam, then we are able to obtain crystal lattice images, which are well defined. And this allows us to do crystallographic analysis of lattice defects. Good. So that's the stage. And now let me motivate why we are interested in this ECCI technique and why it is worth to invest even an hour of lecturing. So this is a picture or a series of pictures of a TEM observation of dislocations. It's actually an in situ observation made by Kondo on a nano indentation in strontium titanate. It's a beautiful experiment, a beautiful paper. And what I want to show you here is, sorry, where is my cursor? Oh, my cursor is not yet properly visible. Yeah, I want the laser pointer. All right. So what you will see here is an indenter, which indents into this perfectly arranged bicrystal. Here is a little grain. Here's a grain boundary, and this indenter is actually indenting into this material. No, it's not working here. Then I need another cursor again. I'm sorry. Go back to the classical one. No, it's not working. Why is it not? Okay, then let's go like that. So what we see here is we are increasing the load on the indenter, and we see increasing amount of dislocations being created in this one crystal, piling up at the grain boundary. And then at one moment we get a so-called here, oops, that was too quick, sorry. Going back, my mouse is not working properly. Let me shortly switch. There we go. Okay, so after a while, we get a so-called pop-in event, and this pop-in event creates a lot of dislocations around this indenter and also dislocations on the other side of the grain boundary. So this is a very interesting experiment, but one could say it's a once-in-a-life experiment. You need everything being perfect. The sample must be at the perfect position. It must, of course, be perfectly simmed. You must have the right crystal orientation for the sample to see the dislocation so clearly. The indenter has to be nicely placed on this very thin foil to get all these beautiful images. Now, I don't claim that we can do the same thing in SEM, at least not yet. Maybe in the future we can, but we get some very similar information by doing nano indentation into materials and observing the effect in the SEM. So in this particular case here, I have placed a nano indenter into a material, then removed the nano indenter and watched what is the dislocation structure around here. And I would first like to point out the magnification of both images is the same. So this 200 nanometer bar, 200 nanometer bar here as well. The size of the indenter is also approximately the same. Here we have a 500 nanometer diameter of the indent. And now what you see here in the SEM image, you see all the dislocations being pushed out of the deformation zone. So for example, you see here is a source of dislocations which emits dislocations in this direction. Here's a second source emitting dislocations in this direction. Here is stacking faults which come up from deep below the indenter and dive to the surface here. So we see a lot of, here's by the way, another dislocation source which emits dislocations into these circular lines here. So there is a lot of information on the dislocations, and you should realize one thing: the crystal, the matrix crystal, appears dark, and that is particular. That means the crystal is in channeling mode. Electrons channel deep into the lattice, and therefore they don't come back out, and the crystal appears black. Only where you have defects, you get interruption of this channeling process, and you see these defects with a white on black contrast or a bright on dark contrast. And the second thing I would like to point out is we indicate here the diffraction vector. The diffraction vector indicates which lattice plane is currently active in creating this image. And this is typical for TEM images, and we can do it now with controlled ECCI also for SEM channeling images. So in this case, for example, the 1, -1, 1 diffraction vector is active. Okay, so far we have not learned much more than in TEM, but now we can go with an SEM situation much further. First thing is we can look in many more grains. In TEM, you usually just can look on very few grains because of only a small area being electron transparent. In SEM, you can look on centimeter square samples if you want. And here I have just selected, I think, 20 different grains. And in each of these grains, I have performed 25 nano indents. And why 25 and not just one? Because I wanted to separate between the stochastic behavior of dislocations and the systematic behavior of dislocations for different orientations. So by looking what is different and what is common between these different indents, I can actually understand what is systematic, what is characteristic for each orientation. So, and you see a second thing, you see this grain is completely dark. That means this one is in channeling mode. Electrons travel into the material and don't come out any longer. While the other grains here, they are in a different situation. For example, this one here is in backscattering mode. It appears very bright. And you will realize that in these situations, you cannot see the defects. You can see the defects only when the matrix is in channeling. And how do we get these grains into the channeling condition? For that, we need to know the orientation of these grains. And then based on this orientation, we can tilt our grains such, or our sample such, that each of these grains is subsequently rotated into or tilted into channeling mode, and we obtain then the defect images. Okay, that's the next nice step. We can test different orientations. We could also go to grain boundaries and then see what they do. But we can go, and we did here, even one step further. And that is, I took pictures of all these images here, and then I removed the indents by lightly polishing, just half a micrometer removal of material removal. And then I charged that sample with hydrogen. So this is actually a TWIP steel, as you see here, a steel with twinning-induced plasticity with high manganese content, charged it with hydrogen and indented then the same grains again. So I could compare what is before and after hydrogen charging. And the result is shown here for 3 different orientations. So actually, you see here an orientation which is selected right from the middle of the stereographic triangle here. And once again, here is the 111 diffraction vector active, selected like that. Now I have indented close to the 001 direction. So we see even the 4-fold symmetry of the indentation direction. Then I have indented into the 111 direction, we see the 3-fold symmetry, and finally indented into the 110 direction with the 2-fold symmetry. Why is this not? Don't know that. Anyway, so we observe many of these grains, of these indents, and then we charge with hydrogen, and we go a step further and look how these same grains, exactly same location, same grains, look before and after. This is before hydrogen, this is after hydrogen. And you see that the pictures have changed quite dramatically. We see some effects which are just caused by the charging of hydrogen, for example, these long stacking faults, which we see here, and also these very special dislocations here. But also we see that the dislocations around the indents, which are really created by the indentation process, have changed. They have changed in curvature. They have changed in extension. That means stacking fault widths. They have changed in number. All of that can now be quantified and observed in a very straightforward manner and with very good statistics. So that's one of the big advantages over TEM. You can observe now hundreds of indents or hundreds of grains if you want, and if you have the capabilities to do that. Okay, so that shall be enough as an introduction on this technique. How do we realize this technique actually? So this is a cross-section through an SEM chamber. And so we have the electron column here, we have the chamber here. And now let me show the first well-known diffraction technique is the EBSD technique. Everyone of you know it. We place a sample here at a strong tilt angle. We obtain on the EBSD detector, we obtain an electron backscatter diffraction pattern, an EBSD pattern. And from that, by scanning over the sample, we obtain this famous orientation microscopy images, which are extremely powerful in information, but that's not our topic today. So the second diffraction technique which we have uses this backscatter electron detector, which sits right below the objective lens. And in order to obtain enough electrons from there, we place our specimen very close to it in the order of a few millimeters only. So we collect as many electrons as possible. And I would like to shortly point out, while the EBSD detector really is a position-sensitive detector, that means every place on this EBSD detector records how many electrons arrive there. The backscatter electron detector here just gets the integral signal of all the electrons which are coming from the specimen. So it has no positional sensitivity. Now, the first thing which we can do is we can rock our electron beam. Not many microscopes do that properly, but some do. And if you can do it, as I show it here, so let me just show it again. So if we rock the electron beam over one well-defined pivot point on the sample, and then plot the intensity which we have obtained for every incidence direction of the electron beam, then we obtain something which is called an electron channeling pattern. And if you compare the ECP with the EBSD, you see they are physically very similar. By symmetry, they are very similar, and even physically, they are almost identical. And yeah, okay, but that doesn't matter. Usually, we don't use this electron channeling patterns because most microscopes don't have a good rocking beam facility. What we do is we do a usual scan, and then we obtain what is called an electron channeling contrast image. And now, why do we get different brightness? Actually, because different grains have different orientation, or you could say have different inclination of the electron beam with respect to the crystal lattice, and therefore grains which are in channeling mode, we will see in a moment what that means, appear in dark, and grains which are in a backscattering mode appear white. And only in the channeling mode grains we see the defects here. Now, in order to obtain a controlled electron channeling contrast, that means in order to know under which conditions do I get channeling, I go ahead in the following way. I first select in an EBSD, I first create an EBSD map. In this EBSD map, I select the grain of interest. Yeah. So I say, for example, I want to look on this grain here. From this, I obtain the diffraction pattern. From the diffraction pattern, I obtain the orientation. From this orientation, I simulate, using particular software, the electron channeling pattern, which I would be able to see if I could create electron channeling patterns in my microscope. So once I have this electron channeling pattern simulated, I go and use this to control the position of my stage, of my sample. And using this controlled position of the stage, I then go and observe my well-controlled electron channeling contrast. Okay, so this is the general procedure that is taken to do ECCI, to do controlled ECCI. And now let me go and explain you a little bit why we see this ECCI contrast. So let me do a little bit of theory. I go quickly through most of the equations, just want to give you a taste, and maybe the TEM people under you will see that we are using exactly the same equations as we are used to from TEM as well. So let me start in a very simple way, in a 2D picture. So you have a set of lattice planes here. Yeah, we see a cut through a lattice plane indicated by their reciprocal lattice vector, which in case of diffraction is identical to the diffraction vector. And now let's put an electron beam falling onto this lattice. And if this electron beam travels under the Bragg angle, so theta here, then the electron beam will be Bragg diffracted. And we can now imagine that the Bragg diffraction will appear again and again and again. And so we can imagine that the electron beam finds its way deep into the lattice when it is exactly parallel, when it's incident exactly parallel to the Bragg angle. And so this is a kind of a total reflection process, as we know it from glass fiber cables. Yeah, glass fibers work with total reflection of a light beam, which travels over many kilometers in a glass fiber with almost no loss of intensity. That's a kind of electron total reflection or electron channeling. Now, what happens during this channeling process is, or better to say, how do we describe this channeling process in a more mathematically proper way? For that, and don't be afraid of this equation, this is the Schrödinger equation for a high energy electron traveling in a crystal lattice. And of course, we won't solve that now, and I also don't go into all details. I just show you this is the sum of all energies of electrons in the lattice. What you see here on that side is the total energy of the electrons. Electrons are described by this electron wave function. And this total energy splits up into a potential energy part, which is caused by the potential of the atomic nuclei. Yeah, so the atomic nuclei are described here. So in this atomic nuclei potential, the electrons have a certain potential energy, and this is the kinetic energy. And now this Schrödinger equation, once we solve it using, for example, a so-called Bloch wave approach, I don't go into details, and we taking the most simple way that says we are assuming only that only one electron beam goes in and is diffracted only on one set of lattice planes. Then we call this the so-called two-beam case here. And under these conditions, the solution of this Schrödinger equation becomes extremely simple. So actually, you see here, this looks maybe, when you see it first, it looks a little scaring, but it's actually a very simple equation, which depends only on one parameter, which is the orientation parameter W. And you can write this equation in 5 lines in a computer code and calculate how much electrons will be coming out, or what the electrons are doing in the microstructure. And this is shown and solved on the next picture here. So where you see here a set of atoms, and we let an electron beam fall onto that set of lattice, or onto that set of atoms. And what the electrons do inside of the crystal is they form a standing wave pattern. That means the wave here indicates how many electrons. They indicate the electron density at every place in the crystal, depending on the incidence angle of the electron beam. And we will see in TEM, we call the effect of that, of the electrons being traveling through, we call diffraction. Oh, here and in SEM, we are actually we are not recording those electrons which travel out on the other side of the crystal, but we are recording those electrons which are backscattered by collisions with the atomic lattice. And what do the lengths of these backscattered electron arrows here mean? Actually, it means that when there is a long lattice, a long arrow, there's lots of electrons being backscattered. And when it is short, that means there is almost no backscattered electrons coming out. And how is this happening? It depends on whether there are many electrons at the atomic nuclei, then we get a lot of backscattering, or there are very few electrons at the atomic nuclei, so the electron density is very low, then we get channeling, and we get very little backscattering. Okay, so, and we call this then channeling in the SEM case. So we are looking from the top side, from the entry side of the electron beam. Good, and now you can imagine if we build in a defect, that means we are disturbing this perfect lattice with this perfect electron pattern on it, then we see a different contrast or a different intensity at this, for example, dislocation here. Then we see it from the surrounding lattice, and that's why we see the dislocations. We will see that in the next pictures. So what do I have here? So let me plot, instead of this moving image, let me plot 3 situations. Why am I always having this bar here in front of me? Okay, so let me plot 3 situations of the electron beam traveling into this lattice. A situation where the electron beam travels under an angle smaller than the Bragg angle, under exactly the Bragg angle, or under an angle larger than the Bragg angle onto this lattice. And what happens then with the electron density, which is coded here in red and blue? So if the electrons travel under an angle smaller than the Bragg angle, that means here our orientation parameter is smaller than 0. Then we have lots of electrons at the atomic nuclei. And as a result, we will get a lot of backscattering, lots of collisions of electrons with atomic nuclei. In the case of the Bragg exact Bragg angle, we have a kind of an intermediate situation. And in the case of an angle larger than the Bragg angle, or W larger than 0, we have no intensity at the atomic nuclei, or only very little, and that means we get channeling. So we have here a lot of electrons being backscattered, here very few electrons being backscattered, and that leads to strong backscattering image. A Bragg diffraction is something intermediate, and little backscattering or channeling. And now we can use this to calculate how much backscattered electrons come out by integrating over these equations, which I showed you before in terms of different depths. And what we obtain is the intensity is proportional to the number of atoms, which you find in this thin slice of Z, proportional to the interaction of electrons with the lattice, with the atoms, so the scattering cross-section, and proportional to the electron density at this slice. And if you do this and integrate over the whole depths, then you obtain for every incident angle of the primary beam, you obtain how many electrons come out. And this is plotted here in this picture here in form of an intensity plot. Here is our lattice. Here is our electron beams under different directions. And now I plot the intensity for different situations. And it's something like that. So close to the Bragg angle, actually a little bit larger than the Bragg angle, we have a very deep minimum channeling, while here in the middle, we have strong backscattering. And here again, on the opposite side, when the electron is in Bragg angle from the opposite side of the lattice, we have again a channeling. And this is exactly what we observe when we observe a Kikuchi pattern or channeling pattern. We have actually here a profile, a dark line, which corresponds to these dark minima here, and a bright band in the middle, which corresponds to this bright Kikuchi band. So in such a diffraction pattern, we actually see the intensity distribution over different incidence angles of the primary electron beam. Okay, and let's skip over that. And I just want to show you the result, which we see, for example, when we look on a polycrystal. Here we have different oriented crystals. And for example, this crystal here is very dark. It's in channeling mode. And that means the electron beam travels parallel to one Kikuchi line, as you see it here in the simulated Kikuchi pattern. This crystal here is very bright. It's in backscattering mode. That means the electron beam travels parallel to a Kikuchi band. You see the electron beam is sitting here in the middle, and we get strong brightness. And the same is for all other grains. We can actually understand from the Kikuchi pattern, under channeling conditions, what is the brightness of these patterns. And that we will exploit later on to see, to obtain controlled imaging. So now so far, we have seen crystals and we have seen kind of ideal situations, but we haven't looked on any defects. So now, but this is actually our interest, is to see the defects. So let me now show what happens when we look on a crystal which has defects inside. And I start with a stacking fault. And for this, let me shortly plot a schematic of a stacking fault. Imagine you have a piece of metal here, and there is this plane here inside. And if we look on the atomic arrangement across this hatched plane, which I have plotted here, you will find that on top of the stacking fault, you have a perfect lattice, here indicated by the blue atoms. Then you have the stacking fault, where actually the order of the atoms is shifted by a fraction of the lattice vector by these partial dislocations here. So that happens at this place here. And then below the stacking fault, you have again a perfect lattice, but it is all shifted with respect to the perfect lattice above. And depending on where you are, this partial dislocation set is at different positions in the crystal. Now, if we calculate what is this, so that means if we put our electron beam onto it and let our wave pattern form, then we get perfect channeling from the perfect crystal, and we get perfect backscattering from the stacking displaced area of the rest of the crystal. And if we calculate now the intensity by integrating over different depths over this channeling and backscattering, we obtain an image which looks like that. More precisely, if we look on top of this crystal with channeling contrast, we see that at the place where the crystal, where the stacking fault comes to the surface, we get a very strong bright feature. And then the deeper we are below the surface, the less intense is the backscattering. And you see it's actually not homogeneously less, but the intensity fades away with an oscillation intensity. So it's bright, dark, and so on. This is very typical. And you will see how does this look in a real live image. So this is, for example, a number of stacking faults observed in a cobalt-based superalloy. And there you see actually these beautiful stripe features here, where they are very bright. The stacking fault comes to the surface, and then they fade away the deeper they are below the surface. And at a certain depth, the contrast completely disappears. And first, they fade away with this typical oscillation structure. Now, in order to get this picture, you must have a well-defined diffraction condition. So this is indicated here with the simulated diffraction image. And in this case here, we use the 002 diffraction vector to create these images. Now, under these conditions, the orientation of the crystal is shown here in form of a stereographic projection. And now I would like to very, very quickly do some analysis of these stacking faults here. Imagine we have this stacking fault here. Yeah, so we see this stacking fault actually falls into the lattice from the right, where it's on the top, to the left bottom. And if we plot its trace into the stereographic projection, we find this goes somewhere exactly through the 111 pole of for this orientation here. Now let's take this one here. It's a stacking fault which travels from the left top to the right bottom, so the opposite direction. And again, we do here the trace analysis, and we find this is again exactly a 111 plane. And then we have further stacking faults, for example, these ones here, they're exactly edge on. And I have plotted already the traces here, and we find it's again a 111. And finally, we have here these ones, yellow ones here, they also exactly follow a 111 plane. So what we see here from this very quick picture only is all the stacking faults are 111 planes, and we can indicate whether they're extrinsic or intrinsic stacking faults. We can learn a lot from just a quick shot here. Of course, we have rotated our crystal first to be at this particular diffraction conditions. And probably those of you who do TEM know how stacking faults look in TEM. They show exactly the same contrast, this typical stripe or fringe contrast, yeah, where you actually, the stacking fault starts on one side of the thin film and ends on the other side of the thin film, so they are limited in width, while here in an SEM image, the stacking faults just continue into the depths forever. Yeah, that's why we see them disappearing. The advantage of the SEM case is we know where is top and where's bottom. While in TEM, we have to do a little tilt experiment to figure out which of these lines here is the top of the sample and which one is the bottom. That means to figure out, is the sample tilt, is the stacking fault tilted like that, or is it tilted like that? Okay, good. Now let's continue. This was stacking faults, and now let's look how dislocations would look like. A dislocation line here, same picture. A dislocation line would, if we intersect this dislocation line atomic structure here in this hatched plane here, we would see the dislocation being indicated by one lattice plane being interrupted, being stopped here, and the atoms below the dislocation line are misplaced with respect to the dislocation, to the atoms above the dislocation line, and that's why we can see them. And if we put our wave pattern, our electron wave pattern on it, we will see actually at the place of the dislocation, the electrons change from channeling to backscattering, and we see a white line. And again, as in the case of SEM, of stacking faults, we see not a continuous disappearance of the white line, but we see an oscillation contrast, as it is also typical for TEM. Okay, so let's look on real images. This is a crystal of a BCC alloy in this particular case, and it's at low magnification. So here just about 8,000 times magnification. The crystal appears completely dark because I have tilted it such that it is in channeling mode. And you see already some white features in this crystal here. And oh, by the way, this is the channeling situation indicated by the primary beam being here on the 101 plane. Okay, and now we zoom into this area here, and we get this beautiful diffraction pattern here. And this diffraction pattern is really, this beautiful diffraction image. And this image is actually full of amazing information. First, let me point out, as we know, what is the diffraction vector? Here is a 1 minus 1, 0 diffraction vector indicated in this direction. Second thing I would like to point out, our dislocations appear with a minimum width about 8 nanometers. So that's about the resolution we can expect from the technique. It's of course not as good as TEM, but good enough to see the dislocations. And what you see now is we have 4 different dislocations here. We have these ones, these long ones. We have these ones which are almost horizontal. We have these ones which are almost invisible. Here's another one, and here's a couple of furthermore. And we have these white dots, which are also dislocations. And now by, again, doing a stereographic projection of this orientation and analyzing these dislocation lines, I will not go in details, but we can do, again, a trace analysis. For example, for these dislocations, we plot the trace inside, and we see this trace travels exactly through a 1 minus 1, 1 pole. That means it's very possible that this dislocation line follows a 1 minus 1, 1 dislocation line direction. Now let me do that for another one, for this blue one. And I plot it here. And again, I find it's again going right through a minus 1, 1, 1, 1, minus 1, 1, 1 pole. And I do it for these little spots here, these white dots. And they are actually exactly coming out of the screen. That means they are in the middle of the stereographic projection. And no surprise, there is another 1 on 1. And finally, these ones here, these almost invisible ones, if we plot it there, it's again going through a 1, 1, 1. And why are they invisible? Actually, because, so we assume that these are all screw dislocations, which follow in a BCC material, the 1, 1, so have a Burgers vector 1, 1, 1 type and follow the 1, 1, 1 line direction. And now if we assume that this is a screw type dislocation with a 1, 1, minus 1 Burgers vector, then the scalar product of G and B, that means of 1 minus 1, 0 and 1, 1 minus 1 is 0. And that's why these dislocations are invisible. And that's exactly what you do in TEM as well when you do analysis of dislocations. So we have done a very quick, very complete dislocation system analysis with a couple of simple pictures here. That goes very well. Now, to illustrate how beautiful ECCI is, let me show you here just another picture, in this case from a high entropy alloy. You see all these fantastic dislocations, which show this typical oscillation contrast here. Many of these dislocations show the back and forth oscillating contrast typical for TEM and for diffraction images. And you see that many of these dislocations here are actually paired. And from this pairing, we realize that the material is not a fully disordered alloy, but there's obviously some linking force between these dislocations, obviously some sort of disordering happening, which links these dislocations into pairs. If you look closer into this picture here, you see these dislocation pairs everywhere. And by modeling these dislocation images, I don't go into details. We use the software EMsoft created by Marc de Graaf and his group. We can calculate how these dislocation images should look like. And from that, we can figure out, is it edge or screw dislocations, or is it partial or perfect dislocations, and then make a claim what actually couples these dislocations together. Okay, enough of that. How do we get so good ECCI images? What do you need to do for that? The first thing is the electron beam must be of small beam convergence. You remember from TEM, you must have parallel illumination to get good contrast. So for good contrast, we must have a small beam convergence. For good resolution, you must have a small spot size, which is kind of in a contradiction with the small beam convergence. And for a good low noise image, you must have a high beam current, which is again in contradiction with a small spot size. So altogether, luckily, we have a number of beautiful instruments, and one of them is the Zeiss Gemini column, which is indicated here. I don't go into details now, but these columns allow actually to combine these contradicting conditions in quite a nice way. And so you get these nice images. There are other microscopes which do that similarly well. And for controlling the position of the crystal, we use a special software which is called TOCA, which I once wrote for TEM. And then, of course, you need a nice flexible stage which allows to tilt your sample. And another lecture would be the preparation of samples, which is quite demanding, not as demanding as TEM, but more demanding than any other SEM technique. Okay, now I'm running out of time, but let me illustrate a couple examples. I hope I still have a couple minutes. So let me show pictures from aluminium. Here, for example, this is a high-strength aluminium which has particles inside, which you see here, overexposed, white big particles which are overexposed because they are heavier than the aluminium. But you see very nicely the twist angle network between the lower grain and the upper grain, the twist grain boundary network of dislocations, which you see here. Here is a different picture, which is a small angle tilt grain boundary network of dislocations here. So we have here, this was screw dislocations. Here you have edge dislocations being aligned to form a low angle grain boundary of tilt character. And what you see here already, some of the dislocations are decorated with little particles, which exactly precipitate at the dislocation sites. And you can see this even on this picture, even more beautiful. You see all these dislocations building the low angle grain boundaries between this grain and this grain. And all these dislocations are beautifully decorated with precipitates because we heated this material after we had deformed it and created this network of dislocations. Right, good. And now let me come to some more worked out examples quickly. The first one is an example on fatigue structures in manganese steels with and without hydrogen, I should say. And allow me to go rather quickly through this material. These high manganese steels are very prone to hydrogen embrittlement. And one result of that is, for example, if you take a high manganese steel deep drawing cup here and you let it stand on your desk for a while, it will start to crack and fold up like a tulip in the spring. And these cracks form at places of highest residual stresses. And the question is actually what does the hydrogen do there in order to actually lead to this crack formation? I don't show you now the full example, but I show you only the approach which we have taken. Hydrogen is generally very difficult to observe in materials. Yeah, so it is invisible to most microscopic techniques. It is very highly mobile, and even if you charge a sample and then run to the microscope, it may have left, or the hydrogen may have left your sample already because it quickly leaves through the surface. So electron channeling contrast is kind of an ideal technique to observe the effects, not to see the hydrogen directly, but to observe the effects. And that is because you can charge and observe bulk samples. That means you can store a large amount of hydrogen inside, and that gives you time enough to run to the microscope, look on the structures, and even do nano indentation, as I showed you before, and still have hydrogen inside. And then you don't need a thin foil, but you are working on the bulk samples directly with ECCI, so you can see the effect of dislocations. And this was the work of Dae-Yong An in his thesis, and I just show you a couple of his experiments. So he did actually shear fatigue experiments under digital image correlation control. And what we did here, you see, now let me jump over. We did a shear experiment like that with a number of cycles. And here you see the DIC approach of this double notched sample. By the way, this is about a 1 millimeter thickness here of that sample. And in this notch area, when we pull and push on that sample, we get a nice and characteristic strain distribution. And this changes with the cycles which we are applying to the material. And now after 50 cycles, after 100 cycles, after 200 cycles, Dae-Yong An took pictures out of that and observed how the dislocations change. So this is, for example, 1 grain after, and then, of course, charged it with hydrogen and did the same experiments. So this is a crystal before cycling, very few dislocations only. This is with 50 cycles, you see dislocations starting to move in there, and this is with 100 cycles. The dislocation densities become higher, and if we zoom in a little bit, you see here the dislocations at 50 cycles, still very rare, and all split up into little stacking folds. And then if we go to 100 cycles, they are more split up, and they start to entangle between different slip systems. And if we continue cycling, then this entanglement leads to the formation of these dislocation walls observed by ECCI in the SEM. And each of these little points here is one dislocation. We can go and calculate what's the dislocation density. For example, here it's 1 × 10⁻14. Then de Jong actually strained the material a little bit more and looked exactly on the same place again, and found that the dislocation density increased by a factor of 5 from 50 to 100 cycles, and so on. And so we could actually make very nice conclusions on what the dislocations do without hydrogen. And also, I will not go into details what they do with hydrogen. And then just to show you very quickly, these are these dislocation walls in one crystal observed by ECCI. And we were now able to combine the ECCI images with stress measurements obtained by cross-correlation EBSD. So cross-correlation EBSD works as follows. You take an EBSD pattern from an unstrained area, and you compare it with an EBSD pattern from a strained area. And then by comparing these two pictures, you can actually calculate the displacement gradient tensor, and from that obtain the elastic stretches and the crystal rotations at these places here. And I just want to show how powerful this combination of ECCI and cross-correlation EBSD is. Here you see an ECCI image, and with the individual dislocations being pointed out here. And along this line, we plotted now the measurements which we obtained with cross-correlation EBSD. That means we plotted the total amount of GNDs, which are obtained from the rotations of the crystal lattice, and the von Mises stresses, which are due to the stretches of the lattice. And we could actually combine both measurements and find out a lot of information, important information on the accumulation of strain in these dislocation walls. Once again, time is too short to go into details, but when we then charged the material with hydrogen, then did the same experiments again, we saw that the material starts cracking very quickly, very immediately. Already after 50 cycles, the material shows everywhere very small cracks here zoomed in, and we could combine, or we could correlate the formation of these cracks with the ECCI images. So there we have it, and understand why these cracks form, under which conditions, and we also know the stresses. What are the stresses to make these cracks opening? Okay, let me skip over the rest for that and just show you a different experiment, which is not yet that. It's it's creep in a single crystal superalloy. Single crystal superalloys, you all know, are used in turbines for airplanes and in gas turbines, of course, as well. And in turbines for airplane turbines, they are employed in this form of this turbine blades. And I should have one here, so they are about that big. Oh, where can you see it here? Oh, you can't see it here. They are about of that size, very small turbine blades. And you all know they have this classical gamma prime microstructure. Zoomed in, we see the gamma prime hard intermetallics and cuboidal intermetallics embedded in a ductile gamma disordered structure. And the intermetallics have here, of course, the L12 crystal structure. And now we did, together with Roger Reed, we did beautiful creep experiments where we took such a newly developed alloy and we crept it at 900 degrees at 450 megapascal, and then took that sample, which had been crept under these conditions, cut it into different portions, and looked onto these different portions all with ECCI. In principle, you could have left it in one piece and just look on different strained areas in one sample. So instead of making thin foils from each of these crystals, we just looked on them. And very important is we looked on areas. So if you look into at low magnification, you see that the superalloy is actually consisting of dendritic structures, which are caused by the single crystal preparation process. And if we look, we have here areas where we have dendrite interfaces, and we have areas inside of the dendrites. And we went exactly to the dendrite interfaces and the internal dendrite areas and looked how the dislocations look like. This one here is inside of the dendrites, and you see beautifully after a certain amount of creep, you see how the dislocations wrap around the hard gamma prime particles here. And if we see a different picture, they are multiplying with increasing strain, and you see them more and more slipping around. And similarly, we can look at the interface between two dendrites. So here's actually one dendrite, here's a second dendrite. We see the interface here, and we can see the dislocations being created by the presence of this interface. And also here we can look inside and see the dislocations being formed there. And now the question was, is the dendrite interface maybe the source of the dislocations which are leading to creep? And for that, we did discrete dislocation dynamic modeling, taking the images which we obtained from ECCI. And I will not go into details. I just show you the results of the modeling here. And we could figure out that the dislocations created at the interfaces play an important role for the development of the dislocations in this material here in general. Okay, last example, no, one quick example in between, and that is we can also go to more complicated materials. And until now, I have shown you examples BCC and FCC mainly, yeah. And now we can go also to materials like what you obtain in titanium alumina. It's used for high temperature applications, also for turbine blades. So here you see the phase diagram. And if we take an alloy which is plotted at this position here, it will be at the temperature where we have annealed it, separate into a gamma titanium aluminide, which is a tetragonal structure, and a hexagonal titanium-3 aluminum structure. And these microstructures are beautifully lamellar. So here are the crystal structures. They are beautifully lamellar if you see them with ECCI or with backscatter contrast, I should better say. Then you see these beautiful lamellar pictures or lamellar structures. And what you see here on the first impression is just mainly atomic number contrast. Bright, let me zoom in a little bit here. The dark areas are the aluminium-rich gamma phase, and the bright areas are the titanium-rich alpha-2 areas. But you see it already on this picture, the darkness is not equal here. This one is not as dark as this one. So this area here is in channeling condition, while this area here is not in channeling condition. And now we can look inside and see with ECCI the beautiful dislocation structures being formed here. We are not yet ready understanding what it is, but if we zoom a little bit in here, you see that we always have a set of 1, 2, 3, 4 dislocations forming one of these stacking faults here. It's always 1, 2, 3, 4 dislocations, partial dislocations most probably. In the gamma, we also see pictures for the titanium-rich phase, for the hexagonal phase. And I just want to show you one beautiful picture which we have obtained recently from the gamma phase again, and where you see this alignment of dislocations forming the stacking faults during the deformation of this material here. Okay, so, and you see also individual dislocations, but very frequently you see these partial dislocations combined with stacking faults or yeah, okay, let's keep it like that. Okay, and then final example now, and that is, it results from, but I think I should stop that. I skip over that. It takes too long. I just
please go ahead, Stefan.
Quickly walk you through some pictures. So this is typical pictures of this additive manufactured material from TEM and observed from ECCI. And you see they are very, very similar, with the advantage in SEM that you have very large samples and you can go to many different places. Instead of zooming in as you do in TEM, you can zoom out and go to different places and learn a lot about the deformation behavior of this material. And we did this, for example, to compare additive manufactured material of a titanium alloy, BCC titanium alloy, compared with an FCC stainless steel alloy. And they form very different structures, and particularly the titanium alloy forms very little dislocations And the question was, why do we have so little dislocations while we have so many in the stainless steel? There is a good explanation, which I will skip over right now. And I skip over that and I come to my last slides. And that's the conclusion. So we have worked on many different materials with ECCI. So we have collected over the last years a large body of experience on metals, preferably. Superalloys give very good images. Steels give very good images. Aluminium alloys, I have shown you nice pictures. It's a bit more tricky. Magnesium alloys is particularly difficult, but with good skill, you can also get nice images there. Titanium alloys, I showed you. Then semiconductors, we have looked into gallium nitride, gallium arsenide, cadmium telluride. Silicon is a bit more difficult because it's so light. Then ceramics, I have shown you a picture of strontium titanate, but I have also recently worked on silicon nitrides, very light ceramics, and saw nice images there. And then minerals, I have also studied already, even including quartz. I haven't had the time to show you. So let me summarize. ECCI is a technique in SEM, which allows TEM-like characterization of extended defects. No? So dislocations, stacking faults, and so on. But in bulk samples with an observation depth of about 100 nanometer below the surface, like in TEM, where you also look for 100 nanometer 6 samples. So the fact that this is a bulk sample potentially enables the defects in a more natural arrangement. So you don't have stress relief. That can be an advantage. That can also be a disadvantage, I should admit. And you can make in situ observations, as I showed you, charging with hydrogen. I showed you deformation. I skipped over the heating experiments. And we can, as I showed you as well, we can see dislocation densities up to the order of 10 to the 14 per square meter. For everything higher, you must conclude the dislocation densities from from EBSD. And yes, that's it. And this final table here compares ECCI and TEM. Of course, resolution of TEM is much better than ECCI. The depth of observation is quite comparable. The observable area in ECCI is, of course, orders of magnitude bigger than in TEM, and that can be a very big advantage if you're aiming for statistically relevant data. And the reason for that is that we are looking on a bulk rather than on a thin foil. And much of this has been published in this work together with Nahid El-Hami in this already 10 years old paper, which is still, however, probably reasonable to read for that. So I am finished with that, and I thank you for holding for almost an hour and listening to me. Thank you very much.
All right. Thank you very much, Stefan Zaefferer from the Max Planck Institute for Sustainable Materials.